Hello, everyone. Today, I'd like to share some of our work in using artificial intelligence to advising the role players in higher ed. To give a quick background, a personal hobby of mine is to write code to avoid the really difficult work like managing academic programs or advising students. So functionality grew over time, and the methods were used at a number of academic institutions to advise their staff and students. So advising at scale doesn't just mean advising large numbers of people. It also means that all role players need good advice, from students to lecturers to program managers to deans and even vice chancellors. Although the advising is quite effective, there are sometimes ethical and moral questions that arise, and I'll walk us through a few case studies and experiences at some institutions. First, at the whole institution scale, we typically want to know how many new students entered the institution, what fraction of those students are graduating in the minimum time, how many graduate in minimum time plus 1 year, plus 2 years, and how many never actually graduate. That's on the left. On the right, we then want to know in which academic programs are we losing those students, and how can we support these programs to improve their graduation rates. So various metrics about these programs start to reveal the type of support that an institution executive can direct to a program, which may lead to a better performance. So once we know which programs need more support and what type of support those programs need, we then need to drill in further, unpacking the reasons for the limited student progression. Besides the general operation of a program, we can look at information about the progress through the coursework. Are there courses where students are taking more time to complete, and are there courses which are attempted much later than expected? There are different types of intervention that can be attempted in all such cases. The slide is not my attempt to draw COVID, or maybe not just to draw COVID. It's a result from one of our algorithms, which shows the routes taken by students mapped with the course combinations that they take. More conceptually, this is how we generate this map. On the y-axis, we have the number of students, and on the x-axis, the fraction of the credits passed. Each node shows a combination of courses, and each edge is 1 semester. We see at the top left, 100 students entered this program, and after 1 semester, only 70 students have passed everything, and 30 students have passed some other combination of courses. After another semester, the star group of 70 students is now a bit smaller, with many students passing a reduced set of courses. So we can do this iteratively and so extract all the routes to graduation and all the combinations of courses and analyze the data to understand the main points in the curriculum where students are taking more time to complete or just exiting the system. We can then also use this data to deduce the academic program. So here we see a structured academic program where the system has highlighted in white where it's correctly estimated the course, and highlighted in yellow is where it got it wrong. And if we look at the reasons for these yellow highlights, we find that there's one single course in the second year with a high fail rate, and this course happens to be a prerequisite to many other courses. So these 4 errors point to one issue in this program, revealing that if more resources are directed to this one course, the progression through the whole program would increase. Even in less structured or even unstructured programs, there is a hidden structure that exists. And we think this grows from the advice that students give each other. And now we can view this hidden curriculum and we can find better ways to support it. A colleague has pointed out that this is how we can find the difference between the curricula that we publish in the handbooks and the curricula actually experienced by the students. So instead of looking at a single module, we can get a ranked list of all the coursework. By knowing the critical regions in a program, a simple timetable shift can often significantly improve the graduation rate, among other types of intervention that we may think of applying. There's a lot that can be gleaned from machine learning algorithms, And here's some data from a US institution. There's quite a lot of metadata and biographical information. We used the same algorithm used by Netflix to figure out what movies we'd like to see based on what movies we saw before. In this case, we use a slightly inverted algorithm to determine which coursework liked which students in terms of the progression rate by the students. In another of our algorithms, we create a model that can predict the likelihood of a student passing or failing a course based on their performance in prior courses. What I like about this algorithm is that it reveals the structures that almost imply the pre and co-requisites that should be in place for students to have the best chances of success. So if we can predict outcomes, the next question is how to broker this as advice to students. Here's an interface from an early version, which I put forward just as a joke initially. So it proposes to say to a student, you've taken extra time to complete the set of courses. Your study is subsidized by the government. By taking this extra time, you've cost the state and the university X amount of currency. This is also an estimated loss of earnings to you of Y amount of currency. To avoid further losses, please pass your courses in the minimum time. As I say, I put this forward just as a joke, but I didn't really hear laughing back. There was just a suggestion that I make the comment about the loss of earnings in bold as well. And with that, people were ready to go. So this interface, although it does make accurate statements about using real data, but I think we have to consider more carefully the message that we're putting out there. At the course level, a lecturer receives advice about better management about his class, the class operations like assessments and events, as well as concept scaffolding and learning resources. We also see a note that advice has not been rendered to students and some metadata is missing. So the system can scan for the presence of such data to ease the process of running classes that have all the materials in place to properly support the students. Further to the lecturer view, we see that the system provides the lecturer with an easy way to generate advice to the entire class of students. A single automated script scans each student's records and deduces the means and standard deviations and uses these to determine which students are performing unusually well or unusually poorly. And it then creates a custom message to each student. The message contains information specific to that student. We find that these custom messages provoke a much stronger response from the students than general messages. Further to custom student messages, this is the interface that a student is presented with when they log in. At the top, we see a note to the students that by improving their performance by just a fraction of a percent, they can raise the class of degree that they graduate with. Even if institutions don't formally grade or classify degrees, the employers do look for such hallmarks. The system in this case is pointing out that the student still has plenty of credits to complete to increase the class of degree. We also see that the system is pointing out in the current semester the courses that the student is registered for. It has calculated, based on the assessments completed so far, what the student has to perform at in the remaining assessments to achieve that higher class of degree. So this form of interface is intended to raise the student goal from merely passing to achieving a better performance overall. By also providing information at the coursework level, it's providing specific actions that should be taken. We note the tempting button, improve my results, and we'll see just now what's behind that. We notice that students are extremely sensitive to any form of interface which presents their results with some kind of classification. In the example shown here, we released an interface showing a report intended purely for degree accreditation panels to use, and adding student access was just an afterthought. We found that the accreditation panel then began complementing the program managers for students suddenly knowing the accreditation criteria for the first time. We generally find that any interface which classifies the progress of a student based on their results will powerfully influence their interest and attention and knowledge about the institution processes. Taking this motivation implication further and accessing the motivation science and gamification, it's possible to use these principles to really drive and direct student behavior. These subsystems yield powerful results. The design of the interface can influence whether class interactions become competitive or cooperative. Since we can predict the performance at a certain level of accuracy, then use such predictions to prompt student action, the next step is to provide the intervention for the student and staff to engage with. There are, of course, general student supports like counseling and general language support and library support and so on. But to really close the loop, we realized that the teaching content also had to be integrated into this process. So this slide shows some of the capacity that our open source content development system, Publon Press, affords. Through this platform, teachers and students can create content that leverages the full range of web content materials like animated simulations, equation rendering, auto-generated assessments, automated grading, and access to a database of learning content. Here's one such element, a meta question. The creator of a meta question is able to build variability into the question so that the system can generate multiple instances of a question to the extent that the text, language, the integration of graphs and illustrations will all differ based on the form of question that the system is spawning. The learner can then practice from a large array of questions and receive immediate feedback in the form of a fully rendered solution memo. This significantly improves the current default approach of only receiving feedback some time after a test or assignment is submitted. From our testing with the system, students have been fully engaged with this content, attempting a far greater range of these questions than was required of them. On the right, we also see a request from a class rep for more of this content for the students. To support this, we released improved editors for more creators to develop such learning content. This can be used by lecturers themselves or by tutors or by the centralized learning design staff that might be at an institution. If we also embrace the concept of students as co-creators, it's also possible to incite the students themselves to develop learning and study content and to share it with the class and possibly be graded on it. This is closely aligned with the principles of open education resources. These projects can be accessed through our nonprofit organization, Modern Scholarship, and through that we host a series of seminars and courses aimed at proper and effective use of best practices among the participating institutions. So we hope the New Zealanders will also join the party. Thanks everyone for listening. Thank you kindly to our hosts for allowing this platform to share this work. Thanks very much.